Any questions about all of this? This is the same slide I showed the other day, but it just went ahead and deleted Monday and changed Wednesday to today. Yes?
How long will commencement rehearsal take?
I was told that I would have students ready to take my test by 11. So if you have an issue, you go talk to them. That's all I can tell you.
I do go to rehearsal then and then
Yeah.
do the test, so it's
Yeah.
no big deal.
Right. That's what I was told. And
Okay. I was just
that's
curious,
all I can
didn't
do.
know how long it was going to take.
I think rehearsal might be 30 minutes, 40 minutes. It's less than an hour probably.
Okay.
You're just going to line up and everything. Yeah.
Okay. I was just curious.
Yep. So, and I can't move it, blah, blah, blah.
No, you're good.
So,
no, you're good.
yeah, you just got to.
I already complained.
Talk to God.
Anyway.
So, all right. Awesome. Well, let's see what else we got. Maybe next. Okay. I know these are review slides, but I thought we'd take a running start at the topic. Remember this one, actually, for this one, you put the Big Bang over here at the right, and then you march forward in time. And then we would be clear out here, remember? Okay. So we have the four forces today. You can kind of see how the four forces separated. And then we actually talked about those four forces in terms of eras. Okay, so this is all review. I think it's pretty cool. And again, sometimes students, and I maybe don't do it justice, don't really believe that this is what physicists, or more specifically astrophysicists, that are in cosmology, which is the beginning of the universe, this is what they know. Sometimes they're like, well, do they really know that? Like, yeah, go ask. I couldn't get one to come and talk to you. We just didn't have the resources. But they will tell you that there is question mark. Like you even saw the question mark on the previous slide with regard to all the forces being one. But those question marks start like the very, very fraction of where all the universe was essentially pointing to. So we have these eras. What's that?
What does that mean, all the forces are one?
It means that, what was it, gravity, electromagnetic, electroweak, and the strong force, they were all one.
One equal force?
Well, and actually to me, then you got it, yeah, one entity, one force, one type, they were combined. So to me, if you're like, well, what do you mean by them being combined? You have to say, well, what do we mean by how they separated? And if you go back to this, what physics says is you needed the universe to cool down in order to make it separate. And so what physics says is that if singularity was honestly that hot and that dense, the forces were combined. See how that works? Cooling down, make less dense, bless you. One of the things that we are studying actually right now in general chemistry too is that the universe likes to disperse matter, spread out matter, and the universe loves to disperse energy. And that's kind of like what happened in the Big Bang. I just think that's so cool. So there you go. Those were all by forces, and these are by particles. Okay, so these are by particles. So the thing is, when it was very hot, you're like, it was too hot. If we're going to do like surf on if they were too hot, then matter couldn't actually stick together. So this is kind of the cooling down. So we got nuclei, and then atoms, and then finally galaxies. This right here, if you want to underline, I kind of emphasize, I kind of pushed it, but it's 380,000 years after the Big Bang. At that point, actually, matter kind of cooled down. It's cooling all the time. Still cooling, as far as I know. And the electrons kind of settled down, so the universe became transparent. We'll say transparent. So speaking of that 380,000 years after the Big Bang, this is kind of showing you where electrons kind of settle down. So from left to right, the left one you see is kind of orangey. And if you look closely, you'll kind of see the little tiny red particles there. Those would be electrons, making it kind of like fog, like opaque, so you couldn't see it. And then it cooled down so that they kind of settle down. And here finally you start to kind of see actually atoms. So that back 380,000 years after the Big Bang, that kind of is a splitting point for us. When we talk about our cosmological horizon, the best we can kind of see is back to that edge. So we're going to talk about that edge. And all things considered, if you take what astrophysicists know, they can actually kind of go back in time and put a temperature on that of about 3,000 Kelvin. Well, one of the things we know about the fabric of space and time is that it's expanding. The universe is expanding. We talked about all sorts of different redshifts, and we actually have this thing called a cosmological redshift, I think we talked about before, where because the fabric of space and time are expanding, these wavelengths get longer. So that would also include infrared, that would also include temperature, thermal energy. So because of that stretch, actually, instead of 3,000 Kelvin, you're looking more at 2.73 Kelvin, which a little bit above absolute zero.
So being that hot way back in the day, was there no visible light then, since the rays?
There was visible light, but it before that 380,000 years, that light was all just kind of, you know how fog, like light is bouncing around, well maybe you don't know, but light bounces around in fog, and the light just doesn't get out. I mean, you are in there and you can see you and somebody next to you can see you, but if you're outside the fog, you're like, I still can't see that person in there. What's happening is that light rays from that person is just being, just being what we call scattered. And so that's actually kind of what happened. It was very bright, I imagine a lot of energy, but we couldn't see it till it settled down.
6,000 Kelvin, that doesn't seem like much.
6,000 Kelvin, yeah, that's like the surface of
The photosphere.
yeah, surface of the photosphere, yeah.
That's what they think the universe started as.
Well, no, that's
Or
what,
380,000 years
that's what, remember we're talking, when did the Big Bang occur? Let's say 12 to 14 billion years ago. So what they're saying is if you go tick, 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 let it cool, let it cool, let it cool, then you get 6,000 Kelvin is kind of our cosmological horizon. That's what it should be at. So you might say, well, I'm going to look for the cosmological horizon to be 6,000 K. Well, not quite so fast. The fabric of space and time over which that signal is traveling gives us a redshift. And so instead of 6,000 Kelvin, you're looking at 2.73 Kelvin. So they could do all that math theoretically. So one of the things about, especially this part of astronomy, is there's a lot of theoretical stuff. And here in a minute, this is a very cool story, I think. The theoretical stuff actually matched up. They were working on that, came up with that temperature, and it matched up with actually an observation that they didn't know until they're like, oh my gosh, it's like the Reese's, I'll take your peanut butter and your chocolate, they accidentally squish and make Reese's, yeah. Well, that's what happened with this topic, okay? So that is so cool. So let me kind of show you what that looked like. I have a video, I think. Do I have a video? Okay. This is actually showing you this wavelength right here, about 1 millimeter. Okay, remember we said that these cousins have something called actually physically a wavelength. Okay, so 1 centimeter, that's about a half an inch. Okay, that energy actually corresponds to a temperature of 2.73 Kelvin. Okay, so here we go. Dun, dun, dun. Let's see if this will work for me. Did you find Waldo here? So what you're looking at here, let's see if I think this has those kind of little, if we were to, that's the signal from our cosmological horizon in radio waves, or microwaves, I guess microwaves, shorter than radio. Okay. And the plank that's in italics here, actually that's a spacecraft. NASA has all sorts of things out there, all sorts of different ways, all looking at different cousins, different wavelengths. So the plank is looking at this microwave background. So anyway.
So is it a circle?
Is it a circle?
Is it like a globe?
Our cosmological horizon is like a globe. And to me, that's kind of just because of where we are and our ability to see, and the information travels at the speed of light. And there was an initial time. And we'll talk a little bit about that with Olber's paradox, I think. But it does not mean that we were in the center. That does not mean we were at the center of where the singularity unfolded, okay, and created space and time. So these little seeds, actually, these little kind of perturbations, it's a fancy word, at the cosmological horizon, those are seeds that can actually create then galaxies, or within galaxies, stars. Those are seeds where matter can come together to create something other than a vacuum. Okay. So let's see. One of the things that actually supports the Big Bang, if we go back to the different eras, one of the eras were nucleosynthesis early on, right after the Big Bang. And during nucleosynthesis, the neutrons, which are gray here, actually were all consumed and formed helium nuclei. So if you look at these red things here are protons. These protons here, these naked protons, are just itching to be hydrogen atoms. This thing right here is itching to be the center of a helium atom. So I was looking at this morning, I'm like, how does that work? So bottom line, within our universe now, not on Earth, if you were to ask how much hydrogen or helium there is on Earth, you'd be like, I don't know, there's probably not much helium. Actually, we're losing helium as we speak. When helium leaves the Earth's surface, it's gone. So anyway, but looking not just at the Earth, but looking at the universe, we're looking at about a 3-to-1 relationship between hydrogen and helium. And anyway, that ratio supports what I just showed you, kind of talking through the steps after the Big Bang. Oops, okay. And we've talked about other elements. Hydrogen is the simplest element. Helium is the next simplest element. Hydrogen has 1 proton, helium has 2 protons, and then it goes up from there. And you'd be like, well, how come we didn't get all sorts of interesting elements at the time of the Big Bang? And the answer is that it cooled, and I think also matter dispersed too quickly. Remember, in order for fusion to occur, you have to have high temperatures and you have to have high densities. Okay. So actually, I have a video to talk about this too. Remember the perturbations I kind of showed you on the cosmic microwave background photo a minute ago at the cosmological horizon? Well, there's this phenomenon called inflation, and I kind of mentioned it on Monday, that inflation is basically where the expansion of our universe, basically it went way fast right away, and then it went way fast, and then it basically now is accelerating. I mean, it slowed down. Inflation was kind of an abrupt sort of expansion. So let's see what this little video says. Now, if I say pause here, the universe kind of confuses me. But this bit right here, you kind of see this A and B. Picture that A and B is basically at the time of the Big Bang. Literally, space A and space B are close together. Okay. Here we have this is the inflation right here, and then here we have just the normal expansion. So here they spread apart this much, and now they're just continuing to kind of spread apart after this right here. So this is inflation. Now what they find is that region of the sky, literally a region of the sky A and region of the sky B have very close similarities. So it looks like A and B used to be close together, but they aren't now. And so kind of one of the things that helps explain that is this idea of inflation. It kind of reminds me of, Pangea, right? We used to have one massive supercontinent. And one of the things that we see now that is kind of cool is if you find, okay, so South America and the Antarctic, okay, there are actually, I think that's one of the examples, there are actually glaciation marks that connect the two. And so that to me kind of they used to be together. Yeah, so it's kind of like that, I think. So the other thing is, what is the shape of our universe? And it kind of has to do with critical density, which is kind of a little bit all over my head. But is that where I go into the next slide? I'll let you find Waldo. But this kind of makes sense, whether our universe is flat or whether it's curved, it kind of depends on your perspective. What this is saying is that if you were to be like a fly or something, your kitten, if you take a kitten and put a kitten on a balloon, okay, the kitten would like take its little paws and kind of curve around with the balloon. But if you were to take something like an ant and put it on the balloon, the ant would be like, I don't know, I don't see much curvature because I'm that big, So it's kind of a bit of perspective there. Oh yes, let's see. Let me put this whole thing up here, and then I'm going to play this video, kind of show you what Olber's paradox means. And it kind of makes sense to me because this idea of an expanding universe and cosmological horizon, that is consistent with the fact that when we go out at night, we don't see the sky like filled with starlight from distant stars. Because if the universe had been around forever, just say, so instead of 13 billion years, let's put, I don't know what forever is, right? Let's put it at 650,000 billion years. I don't know, just very long, okay? At that point, then basically stars have lived their lives, died, and basically they have sent light in all directions, including ours, and our direction. And so basically we wouldn't have any nighttime skies. Our skies would not be dark. Okay? So the fact that they are dark, our skies are dark, means that our universe had a beginning, a definite beginning. So that's how I say it. So let's see what they say.
The battle?
No, the antimatter lost the battle.
Yeah,
Yeah, antimatter and dark matter aren't the same thing.
Oh,
They're different. Yep.
Antimatter ceased to exist.
Antimatter, right. Only in the Large Hadron Collider do we create it or something like that. But antimatter, yeah, in sci-fi movies, yeah. Antimatter. So do these look like galaxies, hopefully? I don't know. Sometimes it's hard to tell a galaxy, but a galaxy kind of has a little fluff to it. Maybe you can see some spiralness or some elliptical galaxies. So yes, dark matter is not the same thing as antimatter. Dark matter, the word dark means you just can't see it. And actually, here Friday, we'll finish up with these notes. And one of the things I'm going to say about dark matter is it could be, it's just not lit up. You're like, it's just regular matter, it's not lit up. Okay, it's possible, but that probably can't be all dark matter is. But we see actually there's dark matter there because it gravitationally influences the stuff around it, the motion of stuff around it, just like Newton's laws of motion say. So there's dark matter and there's dark energy. Sometimes I wish they would have come up with a different term. We have the two dark things going on, okay? But we talked about how actually energy and matter are interchangeable according to Einstein, E is equal to mc squared. And kind of along those lines, if we were to look at the universe, okay, and all that we know about the universe, of course, are we very big? Is the Earth very big in the universe?
No.
No. No, but we're very important, very special. I think so. But if we were to look at the universe, down here in yellow, that's us. Well, I mean, that's not the universe, that's us. Or stars, or I'll just say ordinary matter. Ordinary matter that you see is 5% of the universe with regard to matter and energy. No, are you serious?
That's already so much stuff, though.
I know, there's a lot of stuff that we see, and that's ordinary, so go ahead and scale that up, 5 times, and then you have not the normal matter, but dark matter. And then scale that up, like 10, 12-fold, and you got dark energy. Yeah. I think what's missing from this to me is normal energy, okay? So let's see what this does.